Okay, so actually, I want to be here. All right, so we have a function. Here's the definition. I'll give you the definition in a second. So we've talked about all sorts of functions, right? Linear functions, right? Linear functions have what property? That, you know, if I go get a U-Haul, I buy a U-Haul, it costs $19.99. I pay the $19.99, and then they charge me 50 cents for every mile I drive, right? So for every mile I drive, the price goes up 50 cents. That's linear, because the rate at which it changes is the same every time. That's linear change. And I mention this word change because that's what calculus is all about. Okay, so that's a linear function. So we're talking about y equals 3x plus 5. Y equals 3x plus 5 is linear. What's the slope? Y equals 3x plus 5? 3, right? The slope is 3. That is to say that for every unit that x changes, the y changes by 3 units. Okay. Here, I'm going to talk about a function that changes in a different way. I go and I tell you a rumor about Julie. I say, Julie got into a fight yesterday with the dean and just knocked him stone cold out. I tell you that. I knew that. I tell her that. 2 people know that. We each tell a person that. 4 people know that. They each tell another person. 8 people know that, right? 1, 2, 4, 8, 16, 32, 64, 128, right? Soon everybody knows, right? That change is not the same as linear. That's not going up by the same amount. It's doubling every time, right? Or I could say that it's increasing by 100% every time. It's increasing by 100%. So exponential change is changing by the same percent each time. It's changing by the same percent each time. Okay. We know this more readily when we talk about viral videos, right? The same thing as rumors, basically, right? 4 people watch a video, all of a sudden 15 people watch it, all of a sudden 300 people have seen it, and before a few weeks, 3 million people have seen it, right? This type of growth. When you think about exponential functions, I want you to think about large growth. Like, so at this point, when we're talking about functions that are increasing so much, we're talking about exponential functions. This, of course, has applications in computer science, right? So back in the day, in the 90s, right, I was looking at CompUSA, right, thinking about getting this thing they call a computer, right? And they look at the hard drive. The hard drive was 128 megabytes. The whole hard drive, right? And a few years later, it was, not a few years later, a few months later, it was 256. And a little bit after that, it was 512. A little bit after that, they didn't call it 1024, they just called it a gig. Interesting, right? So they didn't want to write 1024 megabytes, right? They just call it a gig, and everyone thought that a gig meant 1000, but it's 1024. Because it's still a power of 2. All these are just powers of 2. In a similar way, Moore in the early 80s said that not only is that going to happen, not only are we going to double in the amount of space you have on the hard drive, but the space required to hold the hard drive is going to cut in half, so that not only will these devices get bigger and faster, but the space required to hold them is going to get smaller and smaller. And so now we have items right here that are so small but have the same computing power as huge mainframes in the 70s. So the function I've been talking about is a function that goes 2, 4, 8, 16, 32. This function is f of x equals 2 to the x power. So an exponential function is of the form let's do this. F of x equals b to the x is an exponential function. When we look at the picture, please go ahead.
It's like chapter 4.1.
It is 4.1. Thank you. when we look at the picture, is exactly what we would expect it to be. That if at each step, f of x equals 2 to the x, that thing goes crazy. Right? Goes super high, super fast. Right? The 2 here is called the base. B is called the base. Okay. I've introduced a new function, of course. I need to talk about its domain in the range. You can see from the picture. Let me be slightly technical. The base has to be positive, and it makes no sense for the base to be 1. Right. If the base was 1, then you would just have 1 to something, which is always 1. So the base is positive, and the base is not 1. The domain is the set of all values that you can plug into this function, right? In other words, it's how far to the left and how far to the right you can go. How far to the left can I go? All the way, right? How far to the right? All the way. There's a way of writing the whole real line. Domain is the whole real line, minus infinity to infinity. That is to say, I can plug whatever number I want into there, which is what problem number 1 in the homework is saying. So right, it says, what's 2 to the 1.7, right? What's 3 to the 4.298? I can plug whatever number I want, right? So the street version of this, right? So when I talk, I'm going to talk mathematically, and then I'm going to give you the street version, which is what you would just say to someone on the street, right? The street version of this is that when you look at the graph moves all the way to the left and all the way to the right, right? When I talk about the range, the range is about the y-coordinate. How low does this go to how high, right? It won't go below 0. Goes up to infinity. The range is 0 to infinity. Would I include the 0? Does it actually hit 0? No. 2 to any power is never going to be equal to 0. The range is 0 to infinity, not including the 0. Two to the x is one of my favorite functions. Please go ahead.
What do you mean by not including the 0?
That means, thank you for your question. So that means that this graph, right, if I zoom in on it, and this is where the programmer fails. You see the red part of this? It never touches the axis. It never actually hits 0, right? So when I leave out 0, it means that I can have any number greater than 0, but not 0 itself. Not 0 itself. So the way that I leave out 0 is that I put parentheses instead of a bracket. I put parentheses instead of a bracket. So that parentheses. So if I wanted to include 0, I would put a bracket of 0. Remember interval notation? This is interval notation. Okay. Questions about that? This has its, oh, I'm being biased. Of course, I could also do, as Moore alluded to, 1/2 to the x. That can be a base, right? 1/2 is bigger than 0. 1/2 is not 1. I could talk about that too, right? So this is phrased, and I have some element. You'll see lots of word problems like this in 4.4, I think. You have an element, and that it's been decaying, right? Every year you lose a percentage of something, right? You can also think about it in terms of the car that you buy tomorrow, right? Now, early on in college algebra, you know, you'll get a car and it'll decrease in value by $3,000 every year. That's bad, right? You buy the Ford Focus, I'm not saying anything's wrong with Ford, right? But you buy the Ford Focus, right? And it loses $3,000 every year. And then that doesn't really work as modeling, right? Blue Book doesn't use that method, right? Because if you lose $3,000 every year, then if you use that mathematical model, at some point it's going to be worth negative money. And that's really never true. You can always get money for the parts in Ford, right? So that linear way of thinking about depreciation is not going to be effective, right? But if you say instead, oh my goodness, if you say instead that the car loses 20% of its value, every year, right? Then that makes more sense. And then that's an exponential thing, right? It loses 20% of its value every year. So that, in this case, you're losing half of your value every year. So something that starts off at 100, we can make this 10, right? So 10 times 1/2 to the x, right? We'll turn that one off. 10 times 1/2 to the x power, right? Oh, I need to go this way, right? As we might expect, it starts at 0 at 10. 1/2 to the 0 power is 10. I'm sorry, 1/2 to the 0 power is 1 times 10 is 10. So at the beginning, it's 10. And then after 1 unit, it goes to 5. And then 5/2, then 5/4. You just keep taking half of what you had before. The way to phrase that is that you're losing 50% every time. Losing 50% of what you had. Right? So the difference between a linear function is that linear functions decrease by the same amount every time, and an exponential function decreases by the same percentage of what you had every time. Right? That is the difference. This percentage thing comes up, of course, when we start talking about money. Right? So that whenever we're talking about bank accounts and stuff like this, they're talking about exponential functions. Where have I been drawing this? Okay. So, okay, great. Okay, so I think I want to move this, but I'll move it later. Okay. So then, finance. We've got some simple interest. We've got some compound interest. I'm old enough to know when you used to be able to get 3% on a bank account. Those days are very much over now. You go to Ally, right, which is one of the best rates. You can get 0.99% or something like this on a bank account. People still give CDs, which is based on simple interest, right? If I put in $1,000 and then I do 3% simple interest, make it annually, right? They were talking about after 1 year, we're talking about 3% of 1,000, which is 30. In a CD, then they give you the 1,030 back, and then you put the 1,000 in, and then put the 1,000 back in, right? And then you make 1,030, but you've gotten a total of $60 after 2 years. Right? Simple interest. They call those things CDs. Okay. If I put that in Wells Fargo, Bank of America, and just leave it in there in a money market account, then they're going to compound the interest. Right? So that means I'm going to put the $1,000 in. After 1 year, I make 1,030. Right? So I'm going to take the 1,000 plus 30%. I'm sorry, 3% of 1,000. Right? And that's 1,030. But then something else is going to happen if I just leave it in there. If I leave the money in there, then it's 1,030 plus, and then I take 3% of that. 1,030. This is what we mean by compounding. And oh my goodness, financial analysts will say that interest is the most powerful thing in the United States. Right? It just builds and builds and builds. And so in this place, I make $62,500 a year, right? And so I'll take 10% of that for my 401k. 10% of that I'll put towards retirement. George Gwinnett College matches half of that. So that's $900. So $900 every month goes in from a retirement, right? And so I've been here 8 years, right? And so it's easy to calculate what that would be without interest, right? So it's just $900 a month. I get paid for 10 months, $9,000 a year. I've been here 8 years, it's $72,000, right? So just that's how much I have put in, right? The thing now is at $250,000 simply because of interest, right? Simply because interest built, because it takes 3%. Well, actually, I think it's like 4% of what I had before every time. It just adds up, right? So that hopefully I can retire and never have to do anything again. So, but that's not going to happen. That's not going to happen. I'll work until the day I die, right? So, but that gives you an idea of the power of interest, and it also tells you that you should start as quickly as possible, because I would have so much more, right, if I had a 401k all that time that I was in Virginia, but I didn't. I taught there for 6 years, right, and yeah, nothing. They didn't have a plan, but when you work for a state school, they automatically put you into one and all that other stuff, right? Yeah, it's very helpful that way. Okay. That's just, of course, trying to tell you the power of interest. And you can see the power of interest in the way that the exponential function looks. I have to argue to you that this is an exponential function. Let's do a little bit of algebra. After 1 year, it's 1,000 plus 0.03 times 1,000. That's how we got that, right? We can factor out 1,000. These both have 1,000. If I factor that out, it's 1 plus 0.03. 1,000 times 1.03. That's the first year. The second year, I'm going to take that 1,030 and I'm going to ramp it up by taking 3% of that and adding to my 1,030. Well, for the same reason, they both have 1,030 in common, so I can factor that out. And that leaves 1 plus 0.03 yet again. This is equal to 1,030 times 1.03. But 1,030 is already 1,000 times 1.03. So after 2 years, I have 1,000 times 1.03 squared. So I just factor out 1,030. So that's how much you have after 2 years. It's not so hard to see. After 3 years, you're going to have 1,000 times 1.03 to the third. After 7 years, you're going to have 1,000 times 1.03 to the seventh. After X years, you're going to have 1,000 times 1.03 to the X power. We'll generalize this formula in a second, and it'll be on the homework. So this is exponential. And by the way, the street version of why this is exponential is because the variable's in the exponent. The variable's in the exponent. Okay. The general formula for compound interest is this. It's just based off of these ideas. The amount of money you're going to have if you put P dollars into an account with interest rate R compounded N times a year for T years is that. Right? So P, they call the principal, is the amount put in the account. R is the interest rate. N is the number of times you compound. T is the number of years. Here's the first time where we'll actually need to be using a calculator. As you might imagine, the answer to this is going to be a dollar amount. No one's going to want this without you rounding to 2 decimal places, obviously to the number of cents, right? So these are going to be pretty straightforward problems. And so this is one of those issues where you're going to say, well, is this a formula we need to memorize? And if we're doing the problems in my math lab, they usually give you this formula, right? So yeah, so you won't need to memorize this one. So yeah, you'll be given P, R, N, and T most of the time. Eventually, we'll give you A, P, R, and N and ask you to solve for T. And that's just all calculator. All right, so compounded continuously, no one really compounds continuously, but continuous compounding has a different formula. It's A equals P e to the RT. And we'll talk about E. E is a special number in your calculator that is superbly important in calc. Right? So the street version is if you let n go to infinity, then this is the formula that comes up. So continuous compounding is that formula. Questions about this? Domain, range, applications, place.
What's P hyphen say? Oh, amount number.
P is the amount you put in. I put in $P. A is obviously the amount that you get at the end. I didn't write that, but A is the amount you have at the end.
That's a count?
Say it again?
It's a count, right? Amount put in the account.
P is the principal. P is the amount in the account. P is the principal. Thank you. Let's hit the homework. Please.
A equals P-E-R-T?
Yeah. P times e to the RT power.
P times?
E. P times e to the RT power. We'll be practicing this in just a second when we do the homework. 4.1. I believe it's here. First couple, this flat out calculator. The question is, what is 2 to the 1.7 power? TI, if you're using a TI, it's 2 caret 1.7. The only issue is rounding the 3 decimal places. If you're using this calculator here, it's 2, you press this, 1.7, round to 3 decimal places, 3.249. Questions there? 3.249.
So where's the homework going to be open in my math at?
Probably tonight. I'm going to open it tonight. Yep. So yeah, I'm going to upload the videos. The videos take some time to upload. 249. Do the same thing here. 3, this would be 3 caret negative 1.8. Can we see this? Do I need to make it bigger? Who said that? You have the ultimate authority. If you can see it, then we're good. Yeah, so let me just make it slightly larger just in case. Right, that doesn't hurt, right? To the negative 1.8. E is a button in your calculator. I'm not sure it's here unless we make this scientific. It says it is scientific. Oh, there it is, the exponential. So let's clear this. I don't know if it's going to let me do it. Do I have to put in the number first? Let's see here. Yeah, I don't know how you would use the exponential on this simple calculator. But you have an E button on your TI, right? So it's E caret negative 0.69, right? You might want to put that in parentheses. Some calculators give you the parentheses automatically. Round to 3 decimal places. Next couple of problems, just have you play around with these things, right? There's 5 to the x. We know what 5 to the x looks like, right? So this is the other problem with only meeting once a week. We cover a topic, and then in the next hour, I expect you to be an expert on it, right? So when you think about exponential functions with a base that's bigger than 1, just think about it just flowing up. From left to right, it just blows up. When the base is less than 1, you just flip it, it blows down, right? It goes to 0 super quick, right? So here they just want a couple of values. They want them in fractional form. So we're going to put the negative 2 in for x and calculate what that is. They want you to make that a fraction. So 5 to the negative 2 The negative 2 power means 1 over 5 to the second, 1 over 25. 5 to the negative 1, putting in negative 1 wherever there's an x. 1 over 5 to the first, the 1 over 5. Any number to the 0 power is 1, right? Okay. 5 to the first is 5. 5 to the second, 25. And that's not so shocking. Go ahead.
Why is it 1 over 5?
Thank you. So 5 to the negative 1, when you have a negative exponent, it flips the number, right? So when you're multiplying two things, you add the exponents, right? So if I had 5 to the third times 5 to the second, that's 5 to the fifth, right? Is that okay?
Yeah.
Okay. So if I had 5 to the 0, what's 5 to the 0? That's 1, right? 5 to the 0 is 1. All right, so 5 to the first times 5 to the negative 1 is 5 to the 0, which is 1, right? But what's 5 times 1/5? What's 5 times 1/5? What's a fifth of 5? What's 5 divided by 5? That's also 1, right? So 5 times 5 to the minus 1 is 1. 5 times 1/5 is 1. So they have to be the same. Because it's only one number. 5 only has one inverse, right? And it's 1/5 and it's 5 to the minus 1. So they have to be equal. So when you have negative exponents, you just flip it. Negative exponents, you move the denominator.
We're going to like do just that know that, or we're going to get like examples for that.
Now you need to know that 5 to the negative exponent flips it.
Okay.
Yeah. The calculator will help, obviously. Yeah, the calculator will help, obviously. We can't be fooled by any of these. Which one is it? D for sure. And there's so many ways to think about it. The calculus way tells you pretty quickly that it's D because this thing needs to explode. These aren't exploding at all to the right. This one looks like it's going up, just not fast enough. At 2, it's not even 10. We know that at 2, it has to be 25. Right? Once you make the table, it's pretty straightforward which graph it is. The base is less than 1. We know this thing's got to be going down super fast. Half of what you had before each time. Looks like the answer is A already, right? Starts off at 1, half of 1, half of that, half of that. It could be D, but it's not. It doesn't look like it's going down fast enough. Yeah. So
It starts out at somewhere.
what's wrong with B and C?
They go under negative.
Go under the x-axis. Excellent. The range is 0 to infinity. So we can't have any negative numbers there. So that's not B or C. Let's just plug in these values. So again, the algebraic concept is that when you have a negative exponent, you flip it. 1/2 to the negative 2 is actually 2 to the second, which is 4. But again, you can just plug in the calculator for that. 1/2 to the negative 1 is 2. 1/2 to the 0, any number to the 0 power is 1. 1/2 to the first is 1/2. And 1/2 times itself, half of a half, is a fourth. All those numbers go in. And then once you see that, it's pretty obvious because at negative 2, it's 4, which is exactly why this one's right. Questions there? We'll plug in some of these. This will be a chance for us to test our calculator. So there's the formula we were talking about. At this point, when you use the formula, you're just trying to pick out all the relevant things. Looks like find the accumulated value, that would be A, of an investment of $15,000, P, for 3 years, T, at an interest rate of 5%, R. If the money A is A, compounded semi-annually, and is 2, B, quarterly, and is 4, C, monthly, and is 12, or D, continuously, the second part. So let's plug this in. A equals, this is a good time to practice, 15,000, so let's label this, that's P, T, R, as a decimal, n equals 2, n equals 4, n equals 12, and this one is P equals E, I'm sorry, A equals P E to the RT. 15,000 times 1 plus 0.05 over, let's do the first one, 2 raised to the 2 times 3. And the TI goes like this, 15,000 parentheses 1 plus 0.05 slash 2 close parentheses caret parentheses 2 star 3. And for the other ones, you put in 4 and 12. You just do exactly the same thing. For the last one, continuously, the n is gone. A equals 15,000. Use the E button. E to the interest rate is 0.05 times 3. And the TI goes 15,000. E caret parentheses 0.05 star 3. So yeah, I'm not going to do, so B and C left, you just put in 4 and 12 instead of 2 for those. It's all calculator. It's not so surprising they went you to round to the nearest cent. That means 2 decimal places, right?
Can you write the,
Say it again?
can you write the quarterly, monthly?
Sure, thank you. So then this one's going to be 15,000. So this one's semi-annually. Quarterly is 15,000 times 1 plus 0.05 divided by 4 raised to the 4 times 3. And then monthly is 15,000 times 1 plus 0.05 divided by 12 raised to the 12 times 3. Those are all exponential functions. So one of the remarks is that, you know, when you go in to see your financial advisor, they're just using pre-calc, right? They're just using most of the things that we use in society to make tons of money is all before calculus, right? Now, this formula isn't the only formula that you use, right? Because, you know, credit card companies use this formula, right? When you owe something, I was being nice in my examples and saying that you put in money to a bank, but there's no reason for me to say that. I could say, yo, you owed a credit card company $15,000 and they're charging you 19% interest compounded monthly. And if you don't pay any money for it, you can figure out how much you're going to owe. There's no doubt about that, right? So that's the formula. There's no doubt about it. The formula gets a little bit complicated when you decide to pay the minimum amount every month, right? It's slightly different, right? So, but it's just a simple adjustment of this formula, right? And they have it all plugged in and ready to program. So that person you go see simply has a program that they can press a button to see how much you're going to get, right?
What was the monthly again, like the end?
Thank you. So when it's semi-annually, that means twice a year,
Okay.
right? And so quarterly is 4 times a year, and then monthly is 12 times a year. Thank you.
What was the disparity for the compounding continuously?
So then the difference is you use this formula instead. A equals P E to the RT. That's the difference.
And how do you know if you're using that for a
Oh, only because it says continuously.
Okay.
Yeah, it says continuously. Thank you. Good. Other questions? Okay. word problem, classic word problem. This function is going to model the population of a country in millions X years after 1971. Complete parts A through E. How much do you have at the beginning? Right, so if you plug in 0 here, the country's population in 1971, which is the beginning, is 547 times 1.026 to the 0 power, and that is just 547. Right, so the street version is that this amount is always the amount you have at the beginning. Right, that's the street version. Here, we're just going to keep plugging in. $27 for X. So this is all calculated again. 547 times 1.026 to the 27th power. 27 years after 71. Then they want you to find it in 2025. Is that another 27 years? So then 547 times 1.026 to the 54. And then 52, that's another 27 years. 547 times 1.026 to the 81st. And then you can make a conjecture as to what's happening. Something's happening to those numbers. Right? So when you plug those in, you'll be able to answer what happens. Either those numbers are being cut in half, those numbers are doubling, there's no pattern, or it's going by a factor of 3. You'll just be able to see it, whatever it is, right? So just plug all those numbers into your calculator, and then you'll see the pattern of what's happening, and it's one of those 4 things. Right?
Would it be 1/2 though?
You think it's cutting by 1/2? I think the numbers are going up.
Yeah.
The numbers are definitely going up.
Too. That would be B.
It might be B. It's either B or D for sure. Right?
I
It's
thought it
certainly
said increasing by 1/2.
No, it's this one's decreasing. Yeah, growing by a factor of 2. Yeah, it's probably doubling, right? But it might be 3. You just need to see which one it is. Yes, please.
Are you just going through this one so we can do the homeworks later? Or is this,
Yes.
you're just doing it right now? Oh, okay.
Yeah, so yeah, because you're going to get an assignment that looks like this. That's right. Yeah. So that function describes the percentage of information that a particular person remembers X weeks after learning the information. And yeah, you're substituting it again. Okay, so this is after, at the beginning, plug in 0, after 1 week. I think it's by weeks, right? X is in weeks. So this, you plug in 1, plug in 8. 1 year means that you need to plug in 52 weeks, right? So there's the function, plug it in. Just about that. You're going to get, when you plug in the number, you're going to get a decimal, right? And you need to move the decimal place over 2 spaces. Let's do the first one, or this one, I guess. When you plug in 1, we're talking about 80 e to the negative 0.7 times 1 plus 20, 1 week. 80 e to the negative 0.7 times 1 plus 20. Or does it just outright give you the percentage? It looks like it just gives you the percentage. That's good. So it gives you the percentage. How many decimal places? One decimal place. So this one's 59.7. 59.7. So it gives you the decimal. You don't need to move the decimal place at all. 59.7. And then, of course, you can just plug in 2. And that's 39.7. Plug in 52. Right? So decimal is just nice. It just does this stuff just beautifully for you. 20%. Great. That's the first homework assignment. We'll break. Let's take a break for 5 minutes. We'll come back and we'll start 4.2. So I'll stop this recording, and then in the